Okay, so I hope everyone had a good lunch, got refilled for the afternoon. All right, great. My wife is at a conference right now in New York, and she sent me a picture of their lunch. She had a single slice of cheese pizza, and it looked like it had died. So. I didn't want to rub it in. So we're starting just a little bit late, so don't worry, Mike. You have your
I'm all good.
Okay, all right.
I take great pride in my ability to follow directions. You just tell me, okay?
Wonderful. So our next speaker, we are very, very fortunate to have Mike Engelhardt. So for those of you who don't know, Mike has been writing his physical simulators since 1975. His first simulators were written for high-energy physics labs. Instrumentation companies working in charged particle optics and hydrocarbon location for oil exploration. So he has also developed simulators for a number of EDA tools, and today we're going to be hearing about his work with QSPICE. So please give a warm welcome to Mike Engelhardt.
All right, thank you very much. Yeah, whenever I hear that, I always think, God, it's just the gosh darndest thing what a guy will do for a buck. You know, there's no accounting. But okay, so I wrote QSPICE, and people wonder why I would write QSPICE, because many of you know that I also wrote a program called LT-SPICE. And so after having an experience like that, why would I do it all again? And the thing is about LT-SPICE is that I wrote it 25 years ago, and I wrote it in a period of about 10 months. And if you write a project that big in 10 months, there's probably things about it you don't like anymore. And in fact, the matter is there isn't anything in LT-SPICE that can't be done a lot better. So QSPICE is my way of saying, I'm sorry. And I've got it right this time now. So basically, QSPICE started out just as a personal mission to get SPICE right, with no business model, no concerns. I just wanted to get it right once in my life, because it is a complicated code. Even if you're like me and are from UC Berkeley, and you've had someone from the original Berkeley CAD group explain it to you, it's still a complicated code, you know, and trying to figure out why it was architected in that way. I mean, it was like 1970s concept of object-oriented programming, and it makes no sense. Even if you're a native C++ speaker, it makes no sense the way it's written. Anyway, it's a complicated code, room for improvement. But you know, in the 25 years ago, the computer hardware has changed. You would do things differently simply because you would use a different algorithm because the nature of the hardware is different. And there's numerical methods that weren't known 25 years ago. But this is the big thing. We were successful with SPICE simulators. We solved problems, and we don't need to solve the same problems over again. Today, we have new problems to solve. Simulations requirements changed. That's the deal. Okay, so this goes through some details. We don't need to get into this. Let's just jump into why QSPICE is important and why it's going to change your life. Now, this part here is basically SPICE done right. This is basically LT-SPICE, but 10 times better. You know, there's no device IV curve discontinuities. So there's bugs in Berkeley SPICE where the IV curves actually have discontinuities in it. Those discontinuities, even if they're in a unphysical part of where you would ever operate the thing, the simulator doesn't know that it would never operate there and has to iterate through that to find the thing. So if you have discontinuities in value and slope, you cannot analytically iterate to the solution that's meaningful. And I fixed those in QSPICE. The corrected device equations, and actually let me show you how gross some of these discontinuities are. So my mouse is, why is my mouse not working? I'm going to reboot my mouse. Oh, it's working on the display, but not here. Well, that is bizarre. Okay, well, I got it. We got it everywhere here. Okay, great. So this is what I mean. These are gross discontinuities. This is MOSFET channel punch through. Now, sure, gentlemen do not punch through their MOSFETs, okay? But the simulator doesn't know you're not doing that. So if it, in iteration, ends up here, it can't follow this line and end up where it's supposed to be over here. Well, QSPICE has that fixed. Some other SPICEs work like this for the same MOSFET device equations. QSPICE has all of that stuff fixed. All right, corrected device equations. This is what I mean. So these are the output characteristic curves of a JFET, whether you're using Berkeley SPICE or LT SPICE or Peach SPICE or H SPICE or you spend $100,000 on Spectre, those are the device equations. But if you go curve trace a JFET, it looks like this. So the device equations are extended so you can actually properly represent a JFET. And this is actually how I fell in love with KiCAD. I had to measure these curves myself. I made a curve. Standard curve tracers are a little bit hard to use. If you actually want to develop the device equations, you need to use a pulsed curve tracer because you can't tolerate any change in temperature because you're trying to get the device equations and you can't tolerate you have to know the temperature exactly. So even if it's a small signal JFET, you have to put like 10 microsecond pulses, then wait half a second, then do it again. So you have zero temperature rise. And the other thing is that you really need to know the current. So the current measuring was done with a TIA circuit. It's basically done with an electrometer type circuit. So you'd know the current. You didn't have to worry about four-wire techniques. I could just casually connect alligator clips to my device and get these curves. So that's how I fell in love with KiCAD, is making the board for this thing. And it was 8 that took my heart, and the thing that took my heart was the fact it had copper pour that really worked well. It was just a simple 2-layer plated through board with a ground plane, and it did exactly what I wanted all the time. So you can benchmark QSPICE to other simulators, and these are circuits that were collected in academia. They're not some contrived benchmark that I did use QSPICE good. QSPICE is the first simulator I've ever seen that can run every single circuit. These circuits were collected and they found discontinuities in the curves. They didn't work for reasons they didn't understand. They just collected in academia, says we can't solve this IC. QSPICE can solve every one, and they do preposterous things like charge pump the substrate node off into voltages beyond the rails, and they're difficult circuits to solve. Now, the time step control of QSPICE is completely original. It's completely re-architected over any other SPICE simulator. And here is an example that shows what it means. This is a hysteretic switch. So the circuit is a current that charges up a capacitor until it trips the hysteresis. Then it discharges down to a voltage where it overcomes hysteresis in the other direction, so it will charge back up again. It makes an oscillator, okay? And this is actually a desirable circuit to be able to simulate accurately because it only uses one node. And simulation time goes like the number of nodes and not the number of devices. So this is a desirable circuit, but Berkeley SPICE and LT SPICE confuses time step iteration with Newton iteration and can't give you the curve working right. Well, QSPICE just gets all that straight. It understands it. It works fine. Now, a lot of SPICE programs can't simulate this. For example, in PSPICE, it doesn't have a hysteretic switch, and that was to avoid this behavior because they knew they couldn't solve it. Okay, and it kind of floated because the algorithm used in SPICE requires continuous value and slope, and a hysteretic switch doesn't have that. So in the head frame of SPICE, it seems like it's non-physical, but it's not. You can buy a relay, and it's hysteretic, and when it trips or not. And that problem is simply solved. I mean, it's something you can simulate. Okay, so that's one aspect of time step control. And then here is another aspect of it. If you just put in a sine wave in SPICE, every single one of these data points is exactly the right value, to 15 digits, but there aren't enough data points to reconstruct a sine wave properly. So if you run a sine wave in SPICE and then do an FFT, your spurs will be, just 20 dB down, okay? But in QSPICE, it knows exactly how many time points it needs to do so that if you say you want 0.1%, your spurs are 40 dB down. If you want 0.01%, I mean 60 dB down. If you want 0.01%, the spurs are 80 dB down. It has no personality as far as the relative tolerance and the accuracy that you'll get out of your simulation. So that's what I mean by improved type-step control. Now this simulation, so I said that this corner is basically LT-SPICE done right, okay? And this is a LT-SPICE style simulation, okay? This is basically what's inside of the models in LT-SPICE. There's no IP here. I mean, it's not any particular part, and this is all next generation devices. This is what it would look like inside of a Linear Tech part. Let's run the simulation. Now you gotta watch fast. You gotta watch close because it happens pretty fast. Okay, right click. It's done. So in this simulation, so this is the archetypical Linear Tech part. You know, it's peak current mode control, quadratic slope compensation, frequency fold back, and you can phase lock it to an external source. Here's the phase frequency detector, and there's the error voltage on the VCO, and does the soft start, and it comes into regulation there. So that's the point to QSPICE. That's what I was trying to take out as a mission. I just wanted to get SPICE done right once because I knew that LT-SPICE was off by a factor of 10 of the performance that was available. Okay, now, back to why QSPICE is compelling. This here. This actually came because when I developed QSPICE, I was interacting with a number of IC manufacturers, and there are IC manufacturers that make power products that are wildly complicated for the amount of digital logic that are inside of them. I mean, I'm not just talking about I squared C to set the output voltage. I'm talking I squared C communication to set the commutation dead time, the number of pulses used to bring the switch load node to pre-charge the boost capacitor. You know, there's devices with 100 registers controlling 200 values. You know, 100 8-bit registers to control. You know, through divvying up the bit fields, maybe 100 different values, and you just can't do that in SPICE. So what I've done with QSPICE is that you can just draw a symbol, type in some C code, and it includes a C++ compiler, and it will execute that logic as native Intel opcode during the simulation. What I'm saying is the digital logic in QSPICE runs faster than the hardware. I mean, unless you're simulating a Pentium processor, then it's the same speed. It's almost technology. I mean, I don't like to use technology unless you have lithography and ions and bakes and things. So I don't like to call software technology. But this is almost technology. It's a big thing. And you know, it uses the open source Verilator to convert digital Verilog into C++, and then it compiles it with the digital Mars compiler, the free compiler. All that's included. You just install QSPICE, those compilers are included, type in what you want, and it just works. Okay, so now another thing about QSPICE versus LT-SPICE is it has unrestricted licensing. Now, it's not open source. I know a lot of you are going to, you know, they'll grade a lot of you, but, you know, it's not open source, but it is free. Now, by free, I mean everyone can use it, even competitors. You know, the easiest way I can explain the business model of QSPICE is this, and I'm going to do vis-a-vis LT-SPICE. Every electronic engineer has heard of Linear Technology Corporation because of LT-SPICE, but essentially no electronic engineer owns an IC from Linear Tech. They might have designed them in some place, but they don't actually personally own any of them. QSPICE solves a reverse problem that Qorvo had. No one's heard of Qorvo, but every electronic engineer owns an IC by Qorvo because they do the RF for your cell phones. So you all have Qorvo ICs in your pocket right now, but no one has heard of it. So Qorvo bought QSPICE to fix that problem. And in fixing that problem, it's unrestricted. Everyone can use QSPICE. My agenda today is to motivate you to include QSPICE in your KiCAD stuff, and I'll go into, the software technology to do that at the end. Okay, so it has unrestricted licensing, and includes model generator tools. So if you want to use some MOSFET and you don't have a MOSFET for it, it includes separate executables that will help you digitize the data sheet. You just make the data sheet a big, a PDF of your data sheet, a big picture on your screen, and you say where the origin and upper right-hand corner is, set up the scales the same, then you click on points on the curve, and it will make you a model that fits that point. Okay, it will match the saturation and the RDS-on precisely, as well as the body diode and the gate charge. It also nails perfectly, at least as well as the information is available in the data sheet. So you can do that for that. Those tools exist for MOSFETs and for diodes and for JFETs. So that's why QSPICE is compelling. There's one other little aspect to it. QSPICE is, the graphics of QSPICE is based on gaming technology. I mean, if you go into a computer store, or you look at newegg.com, and you look at graphics, or you talk to NVIDIA, it's all about gaming. The gaming business is driven by teenagers' video gaming needs. That's what drives the business. And I've never used any of these games, but I'm okay with the whole thing. I mean, they need faster computers so they can score more points, so they can buy more weapons, so they can kill more space zombies. It's all in the name of progress, But what it means is, when they draw those video games, what they need to do is draw a lot of triangles fast. Okay, the image that the kid looks at, the teenager looks at, is all tessellated into triangles. And that problem has been solved so emphatically by this business that you can draw two right triangles connected with a hypotheses to look like a line faster than you can draw a line. It's unfathomable that you can draw 6 lines and fill them in and shade them and dill them and look like desktop publishing quality graphics faster than Bresciahan's algorithm. It seems like it violates physics, but it does not, because your eye can't see faster in video rates, so it can draw a million of those before a video uprate, and you don't realize that that's what it's doing. Okay, that's the video graphics it lives off of, and it lives off of that for the waveform viewer, so that you doesn't have to compress the waveform data. It can plot out lines, straight lines, 100,000 times faster than a CPU can, and I use that GPU. Okay, so it's using DirectX 12 and 2D2, and the net result is that you have desktop publishing quality graphics for everything, all of the time. All the waveforms, all the CAD, you will never see a pixel. And even a 4K monitor, once you see what it's doing, you can't go back. You can't go back to looking at pixels. I don't know how to explain it. Here's what I mean by beautifully dithered lines. You can't see the pixels. And the waveform viewer is, the user experience is entirely revamped. There's almost no modal dialogues. The problem with a modal dialogue is, okay, you look at a value and you right-click or double-click and a dialogue pops up. You have to move your eyes over to the dialogue, fill out the form, say, okay, and then move your eyes back to the part. I'm not a skeet shooter. I'm an old man. I can't move my eyes that fast on the screen. So if I look at something, that's where I edit it. And all of the, there's more hints. Those hints drawn underneath what you're editing, but everything is edited in place. And the commands are accessed via right-click menus. There's not that many toolbars, not that many toolbar buttons, because the problem with the toolbar, they were great in the 90s. They looked almost like technology. But the problem with the toolbar is you have to move the mouse all the way up to the toolbar, click it, then move it all the way back. And people have shown me how great toolbars are, and I watch them edit their tool, and they're sitting there swatting at the computer telling me how great it is that they have to do that. It's not okay. It's just not okay. Everything is accessed by right-click menus. Almost everything, unless it's an unusual command. I can show some exceptions. Now, importing models is pretty straightforward. Let's see here. Control Q, and then Control B. And if I have a model here, here's a 741. I just take the file, drag and drop it over to the schematic, and it will make the symbol, and I can edit the symbol in place. And I'm going to steal that thing where you resize the symbol, the pins connect. I saw that this morning. I really like that. I'm going to steal that, and I'll have that implemented within a month. That was sharp. I'd like that a lot. I don't know why I never thought of it. But anyway, importing models is drag and drop. It's the same sort of thing where it'll run all the PCSPICE models, and it will, should be able to run them better in PCSPICE. It's a much newer simulation engine. The 45-degree rotations is supported, so you don't need different diodes drawn at different angles. And all these in-place editors work at all the different angles. Here's my little editor, and the full editor's working at every angle. These red dots here is what justification point you want. This little circled red dots, it's justified by that point there. That's the text justification. Everything is in place. And it has intelligent selection guides. What I mean is, say you want to look at a MOSFET, and okay, you may have seen a selection guide that looks like this. You can sort them by RDS on or the gate charge. But the problem with sorting them with RDS on is that if you have a library of a large library of MOSFETs, some are high voltage MOSFETs and some are logic level MOSFETs. So they're, you want to know the RDS on as the part is intended to use. That's an appropriate way of saying this is the RDS on of the part without further information. But what you'd like to be able to do is say what voltage you're going to run it at. It might be even a different voltage yet, and have it just compute the RDS on. So that happens. Say you want to run it at 4.8 volts. You say the gate voltage here, 4.8. You see, a lot of them are infinite because they're not enhanced yet, and you can sort them by the voltage. And that's possible because the same person that wrote the device equations wrote the selection guide. So it has stuff like that in it for intelligent selection guides. For a varactor diode, you can sort them by grading coefficient, which is the parameter that says how fast the capacitance changes with reverse voltage. Or you can sort them by the Q. Zeners, you can sort them by the Zener impedance, not just the voltage. And so on. Oh, and then for like standard parts, you have a standard value, and you can have the 1%, 10%, all the different values will be shown up. There's drop lists of all the standard values, whether it's EN96 or 24 or 12. So the selection guides are all pretty good. Same with inductors. Okay. Okay, and for plotting, this may, okay, so when you're simulating, you want to overlay simulation results. And people that come from a SPICE background know the drill. You write a dot step statement, which will step a user-defined parameter, and then you make a component value depend on that parameter, and then you get to look at the same simulation run with different values for that component. And they're used to that. They accept that. But a lot of times you just have two simulations, you just want to overlay them. So people that come from a simplest background, they just want to overlay unrelated information, and it handles that too. Let's take, okay, great. Here is, I mentioned I fell in love in KiCAD because I had to do a curve tracer, and this is part of the curve tracer circuit. The curve tracer didn't use a PCI data converter. It used the USBs because I didn't want to bring my desktop computer into my lab. I just used a notebook computer. So I was basically digitizing DC levels for but a pulse tester. So I put DC levels on the thing. I would pulse the waveform, and then I use sample and holds to store it long, to store it. And the square pulse was shaped to a Gaussian so that I could use an electrometer type circuit, and the electrometer could keep the virtual ground near ground and not pop a gate while it was working. So that's the way the thing worked. We'll run this simulation. Now the way I do the pulsing is a pretty standard idea. I use a I use a JFET working into the virtual ground of an op amp. And I use a JFET. JFETs are usually used here because they'll have less charge injection for the same RDS(on) as a MOSFET. Standard technique. But if you get to like 10 microsecond pulses, let's look at what this thing looks like. Zoom up on this thing. And you see this is the DC level, and these spikes are the charge injection. Well, that can be handled by, instead of having this end connected to ground, you duplicate the MOSFET over here. And see, when this JFET is on, it's connected to this, this node, the non-inverting input is connected to ground. When it's off, it's connected to ground. But the charge injection is balanced between the two. So if I run this simulation, I can, let's do this one. And I see it doesn't have that problem. And if I want, I can just drag this waveform over to that waveform and overlay them. So you can just, these are unrelated simulations. You might have a peak current mode controller and a constant on-time controller, and they have different transient response, and you just overlay the two. They're completely unrelated things. So you can, you have dot step, and the dot step thing came historically from the fact that was the only way you could get all of the waveform data in the same address space. Well, QSPICE supports an arbitrary number of address spaces. And one of the big things about this also is, say you want to, where is this? Do I have a good example here? That's not a good example. Okay, here we go. So here is a model of a temperature sensor, and I have some measured data here. I can take the CSV file and overlay it onto the measured data. So it's it will overlay CSV files or ASCII SPICE files or binary SPICE files. And you can export your waveform data to any of those formats also. You can just take a fraction of your waveforms and export it into a smaller waveform, or you can export it into an ASCII file, or you can export it to CSV. So all of that is a lot more professionally done now in QSPICE. All right, let's look at a few more examples here. Well, that was the whole curve tracer. It would work for power devices, because it used to be in the silicon carbide devices, and we'd put 50 amps into through a transistor. And this is my electrometer with a half ohm current, TA sensor. Let's see. Okay, so this is a legacy Unitrode type controller. Let's take one that's a little bit more interesting. This is the archetypical Unitrode power supply. 3825, push-pull offline. Here's all your transformers. I'm actually running it voltage mode, but I have a current sense amp. This is done as a hierarchical design, so you can enter into these symbols. These things are just full wave rectifiers. Enter schematic. That's just a full wave rectifier. It's duplicated here for the current sense. Now, here is, let's go into the schematic. The model, you can look at the model, enter schematic, and you see the analog bits, and then this thing here isn't implemented as instanced out gates and flops, but it's just written in C. So you can just look at the source. So this is included an example, and these examples are here to show how to model parts using C++. It's an unusual style coding technique, but it's straightforward, and it's definitely worth learning. So the problem that this is solving, looking at this at a very high level, the thing it's solving is that I told you I wrote LT-SPICE, but I actually also implemented the majority of the switcher models myself personally. And it's laborious to model all those things in LT-SPICE, instancing out gates and flops. So QSPICE solves that problem. You can model easily 100 times faster. You can probably have one individual do all the modeling for a generic S&P 500 company for their parts. It's a big deal. That's the whole point why you want to be able to just mix and mash and spill over into C in the middle of your implementation of your modeling. If you learn how to model in C, no one will be able to keep up with you. There's a number of examples like this. This is actually an MPS part. You enter the schematic. This is an older part, so I actually implemented more with gates and flops, simply because it's easier to read. But in C++, you can access the circuit temperature if you want to. So you don't need this temperature lockout here implemented with circuits. And this is the page of C code is all you end up writing. Oh, and there you can simulate 3 milliseconds of a 500 kilohertz switcher in 2.5 seconds on my notebook. That's the stuff that's, that's what it's about. Yes. Oh, and this is, before I get into how to integrate this with QCAD, let me just say there's one other problem that's solved right in QSPICE, and that deals with the arbitrary capacitance. So here I have a capacitor, and instead of saying, giving it some value, by the way, it does handle capacitance saturation as a native circuit element. You can give it the saturation charge, and it will just model a dielectric, the ceramic capacitor saturation. It will just model that as a native circuit element. But you can, roll your own with writing an equation for charge. And in this thing, this is sort of like a Van de Graaff generator, where you charge a staple and you run it into another voltage. You dump off the charge and you come back. This is what this is a air vane capacitor. And if you put, say, a 9-volt battery to charge it, and then put a motor on the spindle, then as you pull the vanes apart, the charge will be conserved, which means, but the capacitance goes down. So it means the voltage goes up, and then you can make a higher voltage. It's like a generator, except it runs on charge instead of magnets, and you need to prime it with some voltage source. Well, in LT-SPICE, you could write that, but it wouldn't solve it correctly. There's this idea of transcapacitance, where the capacitance between these two nodes, transcapacitance is capacitance at a distance. Let's start with a simpler idea. You know what conductance is? It's the coefficient that tells you the current between two nodes. That's conductance. Transconductance is conductance at a distance. It's the current between these two nodes because of the voltage between these two nodes. And then there's capacitance, which is between two nodes, and transcapacitance is capacitance at a distance. And this is using, and it's something that actually only comes up in making charge modeled transistor devices usually. But this is a transconductance example because the capacitance depends on something else. And it will run this correctly, and here's the output voltage coming up to a couple hundred volts. But this is what, I don't know if there's any real SPICE aficionados here, but people who know SPICE know that if you're going to write a charge model that's complicated, as involves transcapacitances, you don't want to write the equations in capacitances, you want to write it in charge. That's the only way to conserve charge in your circuit, okay? And that's why BSIM is so much more complicated than MOS 1, 2, and 3, is because it has a charge-based model instead of a capacitance-based model. And in the 80s, you would take Berkeley SPICE, replace the charge model, go around all the semiconductor manufacturers and say, look at your SPICE, look at the circuit, see that gate voltage is dropping off to infinity. Now, however, if you run that circuit in our simulator, it doesn't run off to infinity. Your simulator doesn't conserve charge. That's why you pay us $50,000 for our simulator. That was the business model in the 80s for SPICE houses, okay? Well, so this is all based on the idea that you can't conserve charge if you write in terms of capacitances. That's only because you don't integrate the equations correctly. So in QSPICE, I add a corrector step when I'm integrating the differential equations. Here I say the capacitance is based on something, and it conserves charge. And that's basically because I've added a corrector step to the integration of the differential equations. That's original to QSPICE. You can buy this from Spectre or HSPICE or wherever. They don't do that. They just don't have that technology. They don't have those numerical methods implemented in it. All right, that's enough of all of that. Let's get to KiCAD. So the idea is, so QSPICE runs many processes. The schematic capture, now the schematic capture might have many windows because of all the child schematics, okay? But the schematic capture is one process. The simulator is another process, and the waveform viewer is a third process. So, and the interprocess communication is now all completely documented, and I can coordinate with you guys to iron out any problems you have. But the idea would be you would draft in KiCAD, and you would use QSPICE to simulate it. And on Windows, you'd also have a waveform viewer. I can compile the simulator for Linux, but I don't have a DirectX 12 and Direct2D capability in Linux. I mean, there's people that kind of fudge it, but it's not correct. It's emulated with the CPU, and instead of being 100,000 times faster, it's 100,000 times slower. So that's not an option for me. Yes, I understand that you can't be a self-respecting software engineer and use Windows, but you know, if you're agnostic, you just do with what you have to do, okay? And as much as I'm a native C++ speaker, I am a native Windows user. But I was a Linux user in the 90s when I was, you know, and I was the first person to port SPICE to Linux. I understand, but unfortunately, it does not pay the bills. Okay, so this is the idea. This is the way it would look. And what do I have here? Do I have any? Oh, yes. And this is the help documentation. And there's an appendix I've added that documents the interprocess communication. So the schematic capture program basically creates this process. I pipe the netlist to that process, just not to make any temporary file clutter. You could have it you could write it to a temp file and give the simulator the file, the netlist to read, but I just pipe it with an anonymous pipe. Then this is the process you do to start the waveform viewer. And then if you want to run post-processing, you know, like, you know, execute your .measure statements and your .for statements, that's how you'd run the post-processor. And those are all the message numbers. It's who's talking to who and what the two parameters are and a description of what they do. So that's what I'd like to see happen, is you, for KiCAD users, you'd replace the QSPICE schematic capture. Not that I mean, the QSPICE schematic capture is perfectly fine. It's not that great for PC board integration because it doesn't even have multiple parts per package. Okay, it's not a PC board schematic capture tool. But you would use your schematic capture tool and then have QSPICE simulate them. And that's the overall flow of it. Was that exciting? Let's see, is there anything here? Yeah, so what do you guys think? You. Oh, thumbs up is not thinking, you know. I appreciate it immensely, you know, but yes, sir.
Pardon me. Super cool. But I know one of the big principles of KiCAD development is being platform agnostic, and I think that's going to be the main hurdle to adoption here. Is that, you know, I'm a Linux user. I don't own a copy of Windows, and so I couldn't, with the system you're proposing, view any waveforms. And I don't know. That's all I wanted to bring up.
Yeah, I'm aware of that. The choices made for QSPICE came from, that was hit me with two prongs. I understand loving Linux. A self-respecting person doesn't use Windows. I get it. It's okay. But the two prongs that hit me to totally go down 2 feet with Windows, one was that the graphics. is such an important part of simulation, and nothing is close as a Windows. I mean, you know, there's just, you just don't get a direct 2D implementation with a very smart GPU in Linux. You know, people don't put multi-$1,000 cards in their Linux machines. They might to dissipate heat, but they don't get much use out of them, and I use that. That's one reason. The other problem is that I am from the semiconductor manufacturer side of things, okay? And I go and talk to, well, with LT-SPICE, I actually spent more customer face-to-face time than any other person in the industry. I would log about 20,000 hours face-to-face with customers per year because I would travel the whole world. I was on a different continent every month talking to many people all over the world, and I didn't see one person use Linux. Okay, I know that CAD is often towards Linux, but people doing, you know, light industry design of circuits are using Windows. And the fact that they have this technology that isn't agnostic on platform is why I'm in Windows. Okay, that's it. But I love you dearly, but you know, maybe someday, maybe there's a Vulkan method. The OpenGL was a complete disappointment. And it's not like I haven't developed GUIs on other systems. You know, there was a Mac version of LT-SPICE, and I wrote that thing. I wrote the whole thing. I wrote the whole, you know, all of it in the Mac version. And honestly, developing on a different graphics library, the way I describe it was, before I developed on a Mac, I felt that if I were traveling through the universe and came to a different planet, I would be able to tell the difference between life and a rock. After developing on a Mac, I didn't believe that anymore. It was so different. It shattered that belief that I had. And so, you know, maybe the technology will come to Linux and it will be, you know, enjoy some ubiquity and be, yes, this is the solution is going to go. And then maybe at that point, I'll write a waveform viewer for Linux. And actually, the waveform viewer is a lot harder than, I don't want to, yeah, waveform viewer is the hardest thing. And so if I could get the waveform viewer running on Linux, then maybe there would be a Linux version, an agnostic version. But for now, those are the two prongs that hit me. Having spent 20,000 hours per year talking to customers, and where the technology is sitting, what's driving the graphics business.
Yeah, different direction, but I wanted to, I guess, provide an anecdote. So I
loved your talk, by the way.
Oh, thanks.
Just so you know.
Well, so I have two different, actually probably three different things, but we'll just keep it short. I just wanted to say, just to maybe read, you know, provide some, you know, anecdote about, I think about 2 years ago, it was like fall of 2023 that I didn't do it, but one of the guys that works for me, we wanted to do a simulation, basically of like a hysteretic mode current source. Mm-hmm. This was the only thing that could do it with minimal fuss. Like, and the only reason I knew it could probably do it because I had read an article a long time about some of the, you know, the computational methods in LT-SPICE, and you know, that when I heard that you were involved with, you know, QSPICE, I was like, oh yeah, we're going to do it. And it works obscenely well for like nonlinear switching. Then that led on to design of a sigma delta converter.
Oh, okay.
Which, I mean, effectively is kind of the same type of problem. It's just, it's weird. And it's like, to converge on that's hard. The other place, and I don't know, you may have come across people using it, but when I was in grad school, like one of the best courses I had, and he was on my thesis committee, who taught acoustic transduction. And everything we translated basically into a circuit, you know, but it was kind of like a circuit that can model three-dimensional behavior. At the time we used LT-SPICE, and we'd write equations and kind of get it in the system. But there are people doing, electroacoustic, you know, transducer design, you know, but using, because there was one circuit element we needed a gyrator. It's kind of like a transformer, but different, right? It inverts one component. So just to I don't know, provide an anecdote.
Gyrator is a transinductance.
Yeah, it's something that you don't like. You don't go.
It's
to
like an old radio. They didn't have a variable capacitor. They had two in coils, and you would rotate it, and you'd tune the inductance.
You know, when we developed some of the models to model behavior in, radiation and things in acoustics, you actually need that model. It's not like you go to DigiKey and buy it, but just to, it really is for those types of things extremely useful to the point where, for me, like a KiCAD integration would be great, but it's like I always separate problems of, there's the problem of putting things on the page. How do you do that? And knowing what goes on the page. Like this tool helps me figure out what do I actually need to put on the page in my final design. So having two separate is actually fine, but integrated would be great. But knowing that like the numerical methods are just awesome, like the equation solver. So just want to provide that.
Well, thank you for all
Well,
that.
and the Verilog part too, I didn't even know that. So that's the other piece. I do a lot of like HDL and simulation, and that's just really interesting.
There is a big difference between making PC boards and doing circuit simulation, and the thing about circuit simulation is what it does is it develops your understanding of the circuit. Okay, it's how you nurture your intuition, so you can so you know what you need to do to test something, because not everything, you may not have modeled something over temperature, but after you see the circuits and get familiar with it and becomes part of your intuition, then you know what you need to do to test it. I mean, the whole point of simulation is just to understand the circuit better, and so it assists in knowing what to put on the board, what to put there. It assists in that process. It helps flush out the way you feel about what you're choosing. That again, it takes a tangent in what you're saying, but it's when you talk like that, it reminded me of something that people miss. Because people don't know what the point is of simulation. They think it's, oh, that's how you verify design, or someone else might say, well, it's a sanity check. Well, it's not how you verify design. Simulation models don't have production scatter. So what are you going to do? You can't verify your design with simulation. That's abject nonsense. And is it a sanity check? If you're worried about your sanity, you should talk to a therapist. It's just, it's nonsense. The whole point is to cultivate, to nurture your intuition of the circuit. That's the point of simulation. And which is different than getting, the contract done to make the board and make everything work and get paid. It's a different thing. It is a different thing.
I think I'm up next. Just was curious if you'd ever considered, when you were starting QSPICE, if you considered doing an open source piece of software, and what the reasons were that you chose to keep it free but not open source.
The full story there is that I got sick of LT-SPICE and I wanted to make it open source. But I mean, Linear Tech had paid me a buttload of money to write the thing. I didn't own LT-SPICE. I had written it, and I was the only person that wrote it, and I wrote all the models, but I didn't own it. And at that time, ADI had bought Linear Tech, and they didn't like that idea at all, and the result was that I left the company. QSPICE, like I said, it was like my way of saying I'm sorry, just get it right once, the whole thing right. And what the business model would be, I was going to, again, respect ownership. I would sell it to somebody. If they wanted to make it open source, it would be open source. If it wanted to be free for everyone to use, it would be free for everyone to use. In fact, I did not call it QSPICE. I called it SPQR, and I called the company Marcus Aurelius Software, and the simulator was called Caligula, and the waveform viewer was called Vespasian, because you can't trademark these things, and it was a way of telling the person I was going to sell it to that you will name this. Okay? Honestly, I knew the simulator was going to be called Caligula. Everything else was camouflage, because all SPICE programs have evil names. SPICE was originally called Cancer. And Larry Nagel's first job for his master's thesis was to think of a nice name for this program, because the dean says we're not going to have a software project on this company called Cancer. And this is in the 70s, and if you're, you might be able to reflect on what the concept of taste was in the United States in the 1970s and understand there can't be anything nicer than Spice, so we'll call it Spice. It was another in-your-face name. And then other simulators like Spectre, well, it was written after the James Bond novels. There's no way it wasn't named after the evil empire. Like, they all had evil names. So I thought I would call my, why not just finish it and call it Caligula? Be as bad as possible. Because I wanted to completely rethink how a SPICE program should work, completely rethink the time step control. And who rethinks everything more than a despot? For they rethink the very nature of good and evil. It's like no despot thinks they're a bad person. They are who they are. They're not a bad person. They rethink the very nature of good and evil. And that's why it was going to be called Caligula, and that was its code name in-house. And then the waveform viewer was called Vespasian because he built the Colosseum. Real bad guy. Just real bad guy. Maybe even worse than Caligula because he did it on a mass scale. And in Italy, everybody hates Vespasian more than anything, But, the Colosseum is where you sit back and look at everything, It's where you kill those parts with too many volts, So it was going to be Vespasian. And then the post-processor was Romulus, because in Western history, the last legal emperor, last Roman emperor was Romulus, though, the last Roman emperor was actually Constantine in the East. But I called him Romulus to stick with the Western version of history.
So points on Windows, well understood. I had one confusion point I wanted to clear up to understand. You had mentioned briefly the simulator could be possible to compile to Linux, and I was wondering if you had ever considered maybe just compiling a simulator binary for Linux and seeing if the development community could try to tackle waveform presentation.
I have, because of other work I'm involved with, I have it compiling under Linux. If someone wants to write a waveform viewer, it'll be the waveform files are bit identical between Linux and Windows. So you have your test vector. And then if they have a working waveform viewer, let's just go and get the thing, properly operating system agnostic as it should be. Yes.
We'll pass the mic over to you.
So when it comes to designs, when it comes to designs, like things that we simulate are not necessarily the entire design. So like maybe an analog or some active filter or take your pick, right? Can you speak to like best practices when it comes to like isolating the things you want to simulate versus things you don't? Okay,
very good. Excellent. And this is one of the things where there's a bit of a disjoint between PC board design and circuit, the schematics you use for simulation. There's a disjoint there. Now the thing is that engineers break big unsolvable problems into many smaller solvable problems. That's what engineers do, and that's what engineering is. Okay, so if you can break it into a smaller part and understand that smaller part by itself, that's what's the right thing to do. That's good. The risks there, and the reason why you want a simulator that can handle a bigger, smaller part, is so that you don't have to make as many simplifying assumptions, so that the smaller simulation that you develop your intuition on is not a literal representation of the real part. Let me just run an example. So here we have this is actually a Qorvo part. And so you can't do this simulation in most simulators. This is actually an I2C control. I2C is a native circuit element in QSPICE. You just tell it here, what address you want it to talk to and what data it does, and then when this thing when write gets a positive edge, it just spits that stuff out. And so in this simulator, this part is part of a cell tower power supply. It's also used in military radar sets. And I think this one has 62 I2C registers controlling about 100 parameters inside. And it's the soft start. It's how the soft start behavior switches over to a low pass filter if you put a reference, use it as a reference voltage instead. It's the commutation dead time. It's the gate voltage. Here I'm using JFET, so I have to be careful with gate voltage. Anyway, when I run this simulation, that's the I2C clocking in data. Okay, and you know, it has no impact on the simulation speed of the rest of the controller. So that's a half-bridge simulated thing. So what I'm saying is here, I did not. The nice thing about a good simulator that can handle more complicated circuits is you don't have to simplify the thing. You don't have to say, oh, I sent these I2C registers over to the thing. Well, this one actually won't even turn on until you tell it to with a command. Yes, you should always simulate as small a thing as small a circuit as possible, but you have to be careful of simplifying assumptions, and you would like the simulator to make it so you don't have to make it as many simplifying assumptions. You know, you won't see a power IC that's controlled by I2C CAN or SPI, where you don't just somewhere say, oh, these are these values, and you stick it into the back of the part through, you know, as a global parameter. You know, you actually just simulate the literal circuit. So it makes the process less error prone. Now, what I'm trying to say is, yes, break your big circuit into smaller circuits, and then there's a disjoint between the circuit that you use for PC board generation and you're simulating, yes. But don't try to simulate a literal version of that smaller circuit. That would be my advice. And if your simulator can do that, you're ahead of the game. It just makes the process less error prone. I mean, hardware engineering is just like software engineering. You do everything just to make it less error prone. That's the whole front and center part of software design, is you do make this, you know, how can I get this thing working? Yes, with no overhead, but no errors in it. Because that's what takes time, is fixing the problems, fixing the bugs. And in hardware, it's even worse, because then you have to get more boards from China, and then, you know, what are you going to do?
Oh, netlist-wise, is the format the same as for LT-SPICE?
For the mostly yes. The differences would be that the C blocks, there's no analogy in LT-SPICE, and I use the C blocks have variable number of node names, so there's 3 groups of ports encapsulated in what are called gimlets. They look like the German double quotes, because that's not a valid character used in SPICE, so I get to use it for something. So I say, these are the input ports, and then I can say, this is the ground. I can hot deck my logic, so I can say, what's the ground of that DLL, and then I say, these are the outputs. And then the first letter is an O with a slash through it, the Norsk O. It looks like a 0 on a 70s computer terminal. So that would be different. Another difference is that LT-SPICE uses A devices, and QSPICE, I wrote those things over a Memorial Day weekend, and I just really don't want to ever see those things again. They're not, it's not a good, I'm not happy with it. They're not implemented correctly, okay? And you have to go through a lot of convolutions to design large amounts of circuits with those, using those gates and flops. So the A devices are not there. And I don't use the A device for anything in QSPICE in case at some point, I mean, because QSPICE is free, if Analog Devices wants me to include the A devices, I will. But I don't like that mixed mode simulator. I've written a lot of them, and that's one of the worst ones I've written. So I don't believe it anymore.
So you still have, for example, this capacitor primitive in QSPICE. It has a built-in ESR.
Yes.
Okay.
Yes, there's a built-in ESR for capacitors, and then additions there is you can say VSAT for the saturation voltage when you start losing differential. If you have a ceramic capacitor, there's 3 points you can give to have the thing saturating with charge. The initial value, And then you can pick a point here, or say at this voltage you have this much reduction. So it's VSAT and SAT frac. So you can pick any point along here, and then it's the CSAT, the value asymptotically approached. Because if you just use a hyperbolic tangent, the capacitance vanishes at high voltages, and you can't solve the circuit. It's not physical. It doesn't work. So you specify the value asymptotically approached, the initial and any point in there, and then it's going to have the right second derivative through the whole thing. Is it going to match more points? No, but it's probably okay. And same for inductors.
Oh, nice.
Oh, and it has a transformer that has. I can show you the transformer. Here's the thing. I forgot to say this. If you haven't used QSPICE, the first thing to do is run some simulations. So under File, Open Demo, these are just examples contrived to try to teach you something. And here under Transformer Saturation, we see a transformer. And I'm going to run the simulation twice with the load connected or not. And I say and you see if you disconnect the load, the thing saturates. Yet if you connect the load, you pull flux out of the transformer, and it doesn't saturate. So you actually need more current if you don't have the load connected. And there you see the values. It's ISAT and LSAT. What the saturation current, what current saturates it, referred to the primary, and then the turns ratio, and you can pull flux out from as many secondaries as you want. And that's another part that's different. That's actually, it looks like an X, but it's actually a cross. This is not a sub-circuit. It's actually the multiply symbol. I don't know, it's like 200, ASCII 200 something in unsigned charge. And it has also variable number of ports with little gimlets, little German. Here, view. Netlist, there's the X device, and that's the symbol that I mean by gimlet. Okay. And that is collecting the ports. Has to be an even number of ports, because it'll be the primary, secondary, and it doesn't matter how many secondaries you have there.
Thank you.
Okay, if there are further questions, I think that Mike will be available during the break here. But I want to thank Mike Engelhardt for a very inspiring talk.
I really appreciate your interest, okay? I really appreciate your interest. And I'm sorry about LT Spice.